Welcome and thank you for joining us. My name is Carmina and I'm your moderator for today's event. We have about 45 minutes of great content prepared for you with 10 minutes for questions at the end. Welcome, Heidi. The floor is now yours.
Thank you for joining me here today. I am excited to share with you how trends in industry are driving a growing interest in power integrity and why this new field needs simulation tools. You will learn some of the new techniques of analyzing and designing with power rail impedance. We will take a look at understanding the basics of what causes ringing on the power rail and how to design an ideal flat impedance to avoid them. This is an incredible time to be in the electronics industry. Smart devices are rapidly changing our daily lives, and along with smart computing, energy, and autonomous vehicles, we are going to see the creation of smart cities. Smart cities will only increase the demand for faster data rates, lower power, smaller components, and higher levels of integration. Let me start today's talk with a view of current trends. I'm sure that you'll agree that the days of simple design have passed. Simple, single-function devices have been replaced by multifunction, always-on connected devices. Just take a look at the next generation of smart cars, which combine wide arrays of sensors with a powerful onboard computer and complex communication systems that simultaneously connect to everything from the internet to GPS to other cars to traffic lights. The common elements to all these smart devices are new levels of complexity, lower levels of power, packed into small but rugged packages. Quite the engineering challenge. The race continues for faster data transmission, with even the most common of consumer products already providing gigabit data rates. Existing Gen 4 high-speed I/O is in the 4 to 10 gigabits per second range, and Gen 5 has already started with data rates entering the 10 to 23 gigabits per second range. Hard to believe that the next generation of USB interfaces will be running at 20 gigabits per second. 5G networks will provide a breakthrough in wireless connectivity that is needed for the transition to smart cities and the ever-increasing demand for faster data rates. The standards are underway and 5G is now real. Commercialization announcements are already rolling in from the mobile carrier vendors, and the major milestone to have 5G at the 2020 Summer Olympics in Japan is less than a year away. A consequence of this complexity is design and test requirements that are growing exponentially. Take 5G as an example. There are literally 20 times more conformance tests than LTE, which was already a famously complex system. Layer on top of that Wi-Fi, Bluetooth, multiple radios, digital memory, and high-speed I/O. And don't forget the local standards that must be passed on more than 20 different geographies around the world. This complexity strains our current ability to manage design and test configurations and the resulting mountains of data. Failing one of these tests at the end of the product design cycle, such as the CISPR conducted emission compliance tests shown here, can be costly. Retrofits with added filters and capacitors can add to manufacturing costs, while design respins to fix EMI/EMC problems result in product delays with daily lost revenue. It is much better to start early in the design phase to understand and mitigate potential EMI noise sources. All power delivery networks suffer from noise, which is driven by parasitic effects. Whether or not these effects are an issue depends on the specification compliance that is desired, the performance margin built into the design, and the manufacturing and process tolerances. Modern EDA tool sets and methodology allow these EMI noise sources to be simulated and compliance predicted up front. Now let's look at why noise on a power rail is often the cause of a failed specification like the CISPR EMC/EMI tests. Electrical schematics actually hide the complexity of the power distribution network with the use of small ground symbols and power pin net names. Modern high-density printed circuit board schematics have thousands of nets, but it is the interconnected web of the power delivery network that is the foundation powering all of the electronics and at the same time providing a noise path to all the nets in the system. Individual power rails are driven by local point-of-load power supplies, but all of these individual power supplies are connected together to the main power supply and are thus potential noise sources for conducted emissions. The power delivery network complexity continues to increase and has resulted in the new field of power integrity, where power delivery is no longer a DC problem. High-speed digital data requires a fast delivery of power at microwave frequencies. Here is an example of a power delivery network for an autonomous vehicle. Data collection from cameras, radar, sonar, GPS, LiDAR, etc. can easily reach 4 terabytes of data per day that cannot be processed remotely and requires localized processors, DDR memory, SerDes transmitter and receiver devices, etc., each with their own point-of-load power supply. Fast DIDT switching loads from these components can react with any inductance in the power delivery path to create voltage-noise ripple. The amount of allowed ripple continues to decrease as power rail voltages drop below 1 volt to meet low power demands and faster data rates. Let me stop for a moment and explain some of the power delivery network acronyms that can be kind of confusing. A point-of-load, POL, power supply is typically a switched mode power supply, SMPS, with a buck regulator, DC to DC converter design that the microprocessor PCB world often calls a voltage regulator module, VRM. All of these terms are often used interchangeably to refer to the source of power. Power delivery networks must provide clean power to the load. Electronic devices have maximum voltages and ripples specified to avoid damage, lost data, and EMI/EMC failures. Old methods of measuring noise on a power rail often fail to detect worst-case voltage ripple. Here is a picture of a power rail measurement on a real-time oscilloscope. The yellow trace shows the power rail voltage, amplitude versus time, and below that is the corresponding load current, amplitude versus time. The goal of the power rail is to provide a constant voltage even when the current load is switched on and off with high-frequency DIDT transients. To test the power rail, there is the classic step load excitation that is used in most data sheets. When a step load change in current is applied to the voltage rail, then the corresponding response on the power rail is called the natural response. This natural response will often have some ringing, but it decays exponentially. The small voltage ripple generated by the step load could easily pass specs. But what if the load excites the power rail at that ripple frequency? This is called the forced response. It is much larger and is the worst-case ripple on the power rail. The forced response grows exponentially to a steady-state value and can be large enough to cause a device-damaging overvoltage, a failure in data transmission, or EMI noise. Normal operation of the load may never excite this resonant frequency, but digital systems are very wideband, and it is hard to test all combinations of operating scenarios. For example, power-saving modes that turn on and off and bursted data can easily create high-speed digital load transients that extend from kilohertz to gigahertz. Now let's look at how power rail impedance can help find the worst-case noise on a power rail. The new way of testing for the worst-case voltage ripple is to look at the impedance peaks in the frequency domain. On the left is a graph of a power rail impedance versus frequency. The data shows 3 peaks where the DIDT at those frequencies times the impedance will result in a maximum ripple. If an impedance peak is kept below a target impedance, shown with the flat green dashed line, then the voltage ripple at that peak frequency will be within acceptable limits. However, what happens if the second impedance peak frequency is excited at the maximum of the forced response of the first frequency, and then the third impedance peak frequency is excited at the maximum of the first 2? Just like 2 ocean waves lining up together to create a much larger rogue wave, the same thing can happen on the power rail, and multiple resonances can line up to create a rogue voltage wave. Rogue voltage waves do exist, and here you can see one that Steve Sandler, an expert in the power integrity industry, captured with an oscilloscope measurement. The probability may be very low, but most of us flying on airplanes or riding in the next generation of autonomous self-driving cars don't want to take a chance on rogue voltage waves. Power integrity engineers make use of target impedance to design the power delivery across a broad frequency range. This target impedance is a simple estimate using the maximum allowed ripple divided by the maximum expected current step load. In this FPGA example, 60 millivolt ripple divided by 5 amps gives a target impedance of 12 milliohms. Here you see a plot of the impedance versus frequency for a 1.2 volt power rail going to an FPGA with the target impedance mask added in red. This target impedance in red shows the flat region where the power supply and printed circuit board power delivery network must deliver the power to the load. The first breakpoint, around 1 megahertz, shows the frequency at which the internal package die capacitance is starting to provide the power to the load. The third breakpoint shows that the spectral content of the load is rapidly diminishing with frequency, and higher PDN impedances are allowed as the DIDT at those frequencies goes to 0. The PI designer only has control over the range of frequencies covered by the voltage regulator module and the printed circuit board decoupling capacitors. The challenge in selecting the decoupling capacitors is that at milliohms of target impedance, the PCB routing parasitics and component package parasitics can be significant. Simply leveraging the decoupling capacitor recommendations from a datasheet may no longer be accurate. Using EM simulation and decoupling capacitor optimizer as shown here can result in fewer capacitors required to meet a target impedance. It turns out that also optimizing for flat impedance will give the best performance with the fewest number of capacitors needed to meet the target impedance and no possibility of rogue waves. Reliability is also improved by reducing the part count and the corresponding solder joints that can fail. Designing for flat target impedance requires an understanding of what causes impedance peaks that can result in ringing on the power rail. Now let's step through a simple design exercise to show how a power integrity engineer can avoid potential EMI/EMC noise sources in their next power delivery network design. The power integrity engineer must get the power from the voltage regulator to the package die load. Any parasitic inductance in the path can react with the fast-changing DIDT of the load to create noise ripple on the power rail. A simple target impedance estimate shown here is used to determine how low the impedance must be to avoid exceeding the maximum noise ripple specified by the load. This target impedance is the first step in design and is simply the delta maximum allowed voltage ripple divided by the maximum delta current transient. Next, it is important to understand where the resonances come from so that they can be avoided. A common source of ringing on the power rail is from the parallel resonance of an inductor with a capacitor. The inductor stores energy in the magnetic field with the phase of the voltage leading the current. A capacitor stores energy in the electric field with the voltage phase lagging the current. Just like a swing with the energy oscillating between potential and kinetic, the current in the inductor and capacitor can slosh back and forth and resonate. Note that for a resistor, the voltage and current are in phase and there is no energy storage. The root cause of this parallel LC ringing on the power rail can be found by looking at this simple schematic here in the upper left. A simple series RL model of the VRM shows how the active inductance of the voltage regulator module is in parallel with the bulk capacitors. The bulk capacitor also has internal series package inductance that is in parallel with the smaller decoupling capacitors. Using a simple SPICE-type schematic simulation shown in the lower left, the parallel L and C can be excited with the sweep of a 1 amp AC current load to see the impedance versus frequency plot on the right. The simulation clearly shows a peak impedance at the LC resonant frequency. A few basic electrical equations characterize the peak frequency and show that the maximum impedance depends on the sharpness or Q of the resonance. The Q can then be reduced by increasing the real resistance in series with the L and C. This series resistance is very important in designing for flat impedance. Resistors that help reduce the resonant Q are often called dampening resistors or snubber resistors. The impedance plot on the right shows how the 20 milliohm resistance of the VRM dominates at low frequency. Then, as the frequency increases, the upward 6 nanohenry inductive slope of the active inductance of the VRM takes over. This inductance then resonates with the 100 nanofarad downward slope of the capacitor to give a peak impedance of 1.5 ohms. Now I will step through an example of how to select capacitors for flat impedance power delivery network design. Starting with a simple series RL model of the power supply, we can clearly see in the impedance versus frequency plot on the left that the supply has a limited low-frequency bandwidth over which it can deliver power. In simulation, it is very interesting to take the series RL model that created the impedance plot on the left and excite it with the time domain step load and forced responses that we showed earlier. The plot on the right shows this power rail voltage versus time and the corresponding current excitation versus time at the bottom using the right axis. Please note that in order to show both the short duration step load and the longer multiple cycle forced response, that the time axis is in log scale. The spikes in voltage at the rising and falling edges of the load current clearly show that there is reduced power delivery to the load for the high-frequency transients where the active inductance of the power supply is increasing the impedance. The power rail voltage drops by 50% when the step load turns on and then spikes by 50% when the load turns off. In this case, there is no resonance, just a simple increasing impedance that reduces the power that can be delivered to the load at high frequencies. The next step is to extend the frequency range of the power delivery network by adding a bulk capacitor to the output of the power supply. The capacitor provides local charge storage that brings down the impedance at higher frequencies. To get the desired flat impedance, we just need to find a capacitor that will decrease in impedance at the same rate that the active inductance of the power supply is increasing in impedance. The simple equation on the right shows a quick estimate for calculating how much bulk capacitance is needed. It is simply the active inductance of the power supply divided by the target impedance squared. Graphically, this is shown in the plot on the left, with the series RL model of the power supply plotted in black, and then in red, the downward slope of the ideal capacitor calculated from the L over Z squared equation. Adding this ideal bulk C to the output will result in flattening out the impedance at higher frequencies. Exciting this impedance with a time domain current excitation is shown in the plot on the right. The voltage spikes that we saw with the power supply by itself are gone, and the resulting blue trace with no ripple shows how the ideal capacitor added for flat impedance is delivering the power needed for the high frequencies in the rising and falling edges of the dynamic current. It would be great if an ideal capacitor existed, but in reality, one gets a series inductor and a resistor free of charge. The impedance of the capacitor is better defined by the sum of this series parasitic resistance plus j omega times the parasitic series inductance plus 1 over j omega times the capacitance. Looking at the graph of the impedance versus frequency on the right, it is clear that the capacitor only acts like a capacitor below the self-resonant frequency. At the self-resonant frequency of the capacitor, the capacitance impedance cancels the inductive impedance, and it is purely resistive, with a value equal to the equivalent series resistance, or ESR, of the capacitor. Above the self-resonant frequency, the capacitor is no longer a capacitor, and now its behavior is that of an inductor, defined by the equivalent series inductance, or ESL, of the capacitor. Going back to the impedance plot with the series RL model of the VRM, shown in black, we can now see what happens when a non-ideal bulk capacitor is added at the output of the voltage regulator module, or the VRM. The bulk capacitor can only extend the flat impedance as far as the ESR and ESL will allow. Once the bulk capacitor impedance starts looking inductive, another decoupling capacitor is needed with less parasitic inductance. To get a capacitor with lower inductance, the package size and distance to the load is typically reduced. The value of this next decoupling capacitor is also estimated from the simple equation of L divided by target Z squared. But this time, the L is the inductance of the bulk capacitor and any additional path inductance. In this example, the 15 nanohenry active inductance of the VRM is compensated with a 16.4 microfarad bulk capacitor shown with the red dashed trace to extend the flat impedance above a megahertz. Then, a second 1.5 microfarad capacitor is added in parallel to extend the flat impedance past 10 megahertz. The next question a designer has is how high in frequency must the flat impedance decoupling be designed to? How many more decoupling capacitors are needed? The simple answer to this question is the design for flat impedance only needs to cover the frequencies or bandwidth required by the spectral content of the load. That sounds good on paper, but actually getting dynamic DIDT information for a given application is very difficult. It is not provided by datasheets, and it is not easy to measure. However, if a package die model is available, then it can be used to estimate how much capacitance is internal to the package die, and from this capacitance, infer an estimated maximum amount of inductance for the PCB power delivery network that the package die capacitance can compensate for. This is done by using the simple capacitor estimating equation for flat impedance in reverse, and this time solving for the inductance that the package die C can compensate for to get a flat impedance. To demonstrate that the VRM and PCB have little impact on the very high frequency impedance seen by the die, a simple simulation is set up with the package die model connected to the PCB PDN impedance on the input package pin side, and then a load transient stimulus is placed at the output on the die side. The impedance seen by the actual switching transistor at the die can then be simulated. This is the plot in the upper left showing the three different cases for the PDN impedance. The worst case is maximum impedance with no PCB PDN attached to the package die model. Then there's the nominal case for flat impedance PCB PDN attached to the package die model, and the ideal zero impedance case where the PCB PDN is a short attached to the package die model. The interesting thing to note is that it is very clear that at higher frequencies, the PCB PDN has little impact on the impedance seen by the load. The open state with no PCB PDN connected clearly shows the decreasing capacitive impedance slope at lower frequencies that can be used to estimate the internal package die capacitance. This capacitance can then be used to estimate the maximum allowed PCB inductance. Another cross-check for determining how high in frequency the PCB PDN must maintain a low impedance is to excite the package pin of the package die model with 10 millivolts AC ripple and see how much noise makes it through to the package die power delivery network to the die. The result of this simulation is shown in the log-log plot on the bottom right. At low frequencies, the 10 millivolt ripple noise is directly transmitted from the power rail to the transistor on the die. But at high frequencies, there is a low-pass filter effect that blocks the higher frequencies from getting through the package die power delivery network to the transistor at the die. This sounds a little complicated, but if we go back to the design of our simple power delivery network and see what happens when the VRM is connected to the package die model with no decoupling capacitors, it will become much clearer. The plot on the left shows the impedance versus frequency as seen by the load when the VRM series RL model is connected directly to the package die behavioral model. In this case, the package die model was an S-parameter data file from the vendor. The original series RL model is the dashed black trace, and the dashed red trace is the package die S-parameter model. The blue trace is the impedance seen when connecting the two models together. At low frequency is the resistive behavior of the VRM. Then, since there is no decoupling capacitors, only the package die model, we can clearly see how the VRM output inductance in parallel with the package capacitance is creating a high impedance resonance. At higher frequencies, the impedance at the load is dominated by the behavior of the package die S-parameter model. Now we remember from the beginning of this presentation that a peak in the impedance can cause a worst-case voltage ripple on the power rail. The time domain plot on the right shows this exact case. The peak impedance may be low enough to handle a single step, but the forced response at this frequency grows exponentially, showing a worst-case noise ripple. To get rid of this resonance, we need to add decoupling capacitors. If one simply adds a factor of 10 capacitor, like a 100 microfarad capacitor that a datasheet may be recommended, or that was leveraged from a previous design, the impedance peak that was causing the power rail noise ripple can be reduced from the original dashed black trace to that of the blue trace. However, notice that by adding this wrong capacitor value, two more resonant peaks have shown up. The bulk capacitor is the wrong value for flat impedance, and the first peak shows that it is resonating with the VRM inductance. The second, higher frequency peak is the capacitor's ESL resonating with the package die capacitance. These two peaks are smaller, but may still not meet the required target impedance and leaves the possibility for a rogue wave. Each of these peaks will require additional capacitors to get to the desired flat target impedance. Eventually, enough capacitors can be added to drive the impedance below the target impedance. However, there is a better way that can maximize performance and minimize cost at the same time. Instead of just leveraging a suggested capacitor value, what if we use the simple L over target Z squared equation to get the C required for flat impedance? Now we might get lucky and only need one capacitor to flatten out the impedance. This clearly shows that the number of capacitors can be reduced by designing for flat target impedance. The time domain plot on the right also shows that flat impedance, solid blue trace, gives less ripple than the non-flat impedance. This design example is a good starting point, but as mentioned earlier, for a real system, the PCB and component parasitics can be significant, and additional tools and measurements are needed to design and test for the final product. Finally, let's take a look at the complete power integrity workflow. The full power integrity workflow might look more like what is shown here. Designers start with good models of the VRM, the decoupling capacitors, and the load. Often, the best models are measure-based models, such as a state space average model of the VRM, or a measured S-parameter of the capacitor. Next, pre-layout investigations like the one we just did enable the designer to understand the challenges and provide layout guidelines. Once the PCB layout is done, a post-layout full EM simulation can be done, and then the result used to optimize the location and values of the decoupling capacitors. A final post-layout PI ecosystem simulation then connects the high-fidelity VRM model with the PCB EM model, the optimized decoupling capacitors, and the package die model to look at both small signal AC impedance and load transients, as well as large signal DC to DC converter switching ripple. The final step in the power integrity workflow is measurement to verify that the ripple is within specification, that load timing and amplitude jitter is acceptable, and that EMI/EMC standards are met. This power integrity workflow looks great, but I am sad to say that there are many designers out there that just leverage a previous design or a datasheet example and wait until measurement to debug. This can be very risky and an expensive way to design. Some engineers use free tools provided by the power supply vendors like LT-Spice, but then they fail to simulate the EM parasitics of the printed circuit board and decoupling components. The PCB industry is focused on post-layout, since this is often where a manager needs to sign off and verify that the design is ready for fabrication. Starting at post-layout EM often leads to the optimization of a bad design. It is better to start with pre-layout to get to the right design space before going to layout. Combining simulation tools for power integrity and power electronics covers the whole power integrity ecosystem from generation to delivery at the load and allows the designer to go through the complete design flow to avoid late in the design cycle failures. An example of why the power integrity workflow needs EM simulation is shown here. The simple rule of thumb of selecting a capacitor using inductance divided by target C squared is a good starting point to get in the right design space, but the actual selection of capacitors is not so simple. The C value you are looking for with the right C, ESR, and low inductance may not exist in a datasheet, and so it is typically necessary to parallel capacitors to get closer to the desired value. However, paralleling capacitors is a bit tricky. The physical location and the measurement points can result in some odd behavior. This simple PCB has 5 side-by-side capacitors mounted and a connector at each end for measurement. You might expect that paralleling 5 identical capacitors will result in 5 times the capacitance with 1/5 the resistance and inductance. But due to small parasitic inductance in the circuit board, the parallel capacitors have a more complicated behavior. Here we have the results of simulating 5 1 microfarad capacitors in parallel and comparing the results of the SPICE simulation of the schematic versus a simulation that includes the printed circuit board EM model. For reference, the single 1 microfarad capacitor impedance is shown in red. The blue trace for the EM simulation of the 5 capacitors in parallel shows that while the capacitance is 5 times greater than the single capacitor, the resistance and inductance are only halved, and they are not the same as the dashed black trace result for the lump SPICE simulation of this schematic. An EM simulation is the best way to get the optimum decoupling design. Instead of loading 5 identical capacitors in parallel, we can also look at 5 different values to see the difference in simulation between the SPICE schematic model and one that includes the EM model of the printed circuit board. Here we show 5 decade-spaced capacitors in parallel, and again we see a large difference at the high frequencies between the lumped SPICE schematic simulation and the simulation with the EM model of the PCB. The SPICE simulation is the black dashed trace, and the red and blue traces include the EM model of the PCB. This result also shows that there are 2 plots for the EM model, one measured at the VRM and the other at the load, and they are not the same. The schematic-based SPICE model does not capture this location dependency of the measurement and shows the same impedance at the VRM and load. This clearly illustrates why EM simulation is needed for optimizing the power delivery impedance at the load. Incorporating EM simulation in the design flow is much easier than it used to be. Tools like PIPro that are built into PathWave ADS are designed to import ODB++ or .brd files with stack-up definition, net names, and components that can then be used for faster setup of EM simulations. Here is a demonstration of PIPro showing the layout of the imported .brd board into ADS layout and the imported stack-up. Opening the PIPro generates a 3D view of the PCB. The nets and component navigation tree make it easy to select the VRM, sinks, and components and assign them to the desired analysis, DC, DC electrothermal, or AC. This is also the same environment for SIPro for the EM simulation of high-speed signal nets, where power and signal nets can be combined into a power-aware EM simulation for applications with large, simultaneous switching noise transients like DDR memory. Starting with DC simulation makes it easy to verify setups, and then the analysis can be copied to an AC simulation to generate the EM model for evaluating the decoupling capacitor performance. The finite element-based EM technology used by PIPro creates ports for every decoupling capacitor so that once the EM model has been calculated, the values of the decoupling capacitors can be changed without rerunning the EM simulation. This makes it easy for the decoupling capacitor optimization tool to analyze multiple capacitor values to meet a user-supplied target impedance with additional constraints for quantity, cost, and number of part values. The EM model with the optimized decoupling can then be exported back to the ADS in the form of a schematic with all of the capacitors and components connected. This EM model can then be connected to the VRM and sync models for an end-to-end PI ecosystem simulation. Obtaining a good VRM model that can be used for an end-to-end power integrity ecosystem simulation with small signal and large signal effects is demonstrated in the YouTube How to Design for Power Integrity video on modeling DC-to-DC converters by Steve Sandler of Picotest. State space models simplify the definition of the control loop behavior, providing accurate small signal output impedance and power supply rejection ratio. The duty cycle output from the state space model is used to drive the large signal switching transients. The video shows how a few simple measurements can be used to create this measure-based VRM model for connection to the PCB power delivery network and load. In order to be able to get simulation to measurement correlation for the performance of the power delivery network, it is best to include the whole power integrity ecosystem of the VRM, the distributed power delivery network with the PCB and decoupling capacitors, and the package die sync-it model. The hierarchical schematic in ADS makes it easy to connect each of these models together, and then in the same schematic we can define multiple simulations, DC, frequency domain S parameters, and harmonic balance. The harmonic balance is very useful for DC-to-DC converter simulations where fast frequency domain simulations can be done at the harmonics of the switching frequency, and then the result converted back to the time domain for looking at the large signal switching transients or ripple. Here are some of the key tools for simulating and measuring the power integrity ecosystem. EM simulators like PathWave ADS PIPro with DC IR drop, AC impedance, and decoupling capacitor optimization enable the design of low impedance power delivery networks. Frequency and time domain schematic simulations along with measure-based models enable end-to-end simulations to explore both small signal noise sources and large signal switching noise ripple. The need for simulation is only going to increase with the next generation of wide bandgap semiconductors, like gallium nitride shown here in the upper right, where high-frequency megahertz switching is pushing efficiencies to 99% and more than doubling the power density to over 1,000 watts per cubic inch. The corresponding measurements are shown on the bottom. The E5061B network analyzer with two-port shunt impedance measurements can go down to microohms of impedance. The real-time Infinium oscilloscope with power rail diagnostics, and the CX33000 current analyzer for measurement diagnostics of the current load transients. I would like to leave you with one last thought and a short history lesson that shows how expensive it is to find a design flaw at the final measurement step of the design process. The original design of the transatlantic cable looked simple, what could be so hard about stretching a wire between a transmitter and a receiver? However, after the huge expense of installing the cable across the Atlantic, the first test in 1858, it was discovered that the signal quality was so poor that transmission had to be slowed down to an almost unusable speed. The cable was destroyed the following month when Wildman Whitehouse applied excessive voltage to it while trying to achieve faster operation. Where was the signal integrity and power integrity engineer in 1858 to explain transmission line impedance? Just like the transatlantic cable, designers today may think that leveraging designs and post-measurement fixes will do the trick. So I ask you, are your designs still leveraging decade capacitor values? Are failed designs band-aided with added filters and more capacitors? Where is your power integrity engineer? That ends my presentation, and I thank you for joining this Keysight educational webinar.
Okay, so now it's time for the question and answer session. So Heidi, here is your first question. This one comes from Dan. Where can I find more information about power integrity examples?
One of the best places to start is the How to Design for Power Integrity YouTube videos that I mentioned in the presentation today. Specifically, we talked about the one on modeling the VRM, but there's a 5-part series, and it will go through a lot of the concepts that we talked about today and walk you through the whole process of how to design for power integrity.
Great.
We also have, real quick, I wanted to mention, we also have some great examples built into PathWave ADS, and in addition, the support website, if you go to PathWave ADS support, we call it the Knowledge Center, and if you log in there, we have some additional examples for power integrity, and that link is provided for you with your resources link here on this webcast, as well as the link to the how-to videos. So thank you. Yes, good question.
Great. I was going to add that. It's in our resource link widget. Thanks, Heidi. Okay, so here's your next question from Shin. Why is it important to start at the VRM with the bulk capacitor when selecting the decoupling capacitors?
It is important to start with the bulk capacitors because we mentioned in the video here that the VRM is actually a control loop and has limited bandwidth. And that control loop can actually go unstable if it doesn't have the right load with the correct ESR attached to it. So this is a very important reason to start with the bulk capacitor and maximize the amount of capacitance in the bulk capacitor with that stable ESR value and load to prevent the VRM from oscillating, which will cause noise on the power rail. This limits the amount of small high-frequency decoupling capacitance that's needed, and it's those ceramic capacitors that often have very low ESR that is much more difficult to control, and too many ceramic capacitors with very low ESR can often cause the VRM to go into oscillation. So I recommend maximizing the bulk capacitor at the VRM with the correct ESR for stability, and then move on to the higher frequency decoupling capacitance provided by the small ceramics.
Great, thanks. And here's a question from Elsa. If you have several parts that load the VRM, how do you keep the impedance flat at each component?
Another good question. Like we just mentioned, you make sure that you've loaded the correct bulk capacitance to maintain good stability with the power supply and have the correct ESR for flat impedance. But as you move out to each load, when you have multiple sinks or multiple loads, you'll find that each one may have a little bit different distributed parasitics getting to that load in terms of the series resistance and the series inductance. It's that parasitic inductance getting to each load that causes a lot of the problems, because of the fast LDIDT times that inductance can cause excessive voltage ripple. So each load will need to have, the correct capacitance to compensate for that inductance getting to that load. And within PathWave ADS, we have our EM simulation tool, PIPro, that lets us actually look at the impedance at each one of the sinks and make sure that we've optimized the capacitance correctly and have the capacitors located in the best position or best location to minimize that inductance of getting to that load. Thank you.
Sure. Okay, so here's a question from Steve. Does it matter where the decoupling capacitors are placed?
Another good question on decoupling capacitors, and it's very one of the frequent questions that we get, because we always want to reduce the number of capacitors and place them where they're needed and most effective. So in terms of placing capacitors, let's go back to the first, or actually the second question we had. Again, we need to optimize the bulk capacitors to maintain the stability of the VRM, but more important, we can look at it kind of in a different way. We need to make sure that the power supply is stable and that we minimize the switching ripple coming from that supply. So we want to make sure that we mitigate or reduce the noise at the source of that noise. So we make sure that our bulk capacitors are correct to avoid oscillations from the VRM, and we make sure that we have any additional capacitance that we need for, say, to reduce that switching frequency ripple. But the next source of noise that we have is actually the load with its fast DI/dt transients. So if we want to mitigate the noise of those switching transients, then we need to place capacitors near to the load, and that's where the high-frequency capacitors come into place. And so I would say there's the two main spots are, one, for the power supply stability and switching ripple is near the VRM as close as you can to mitigate that noise. And then you move as close to the load as possible to start placing the higher frequency capacitors and keep the high frequency switching noise local to that load and mitigate that problem there. Thank you.
Sure. Here's your next question from Naveen. If the datasheet doesn't provide the active inductance of the VRM output, then how does the designer find this value for calculating the bulk capacitor for flat impedance?
This is a trick that I learned from Steve Sandler, our expert in the power integrity industry, and he's actually written a book on power integrity and the measurements that can be done. He sells a lot of test accessories for doing this, but it's actually pretty simple. All that we need to do is power up the VRM and measure its output impedance, and then turn the VRM off. And what happens is if you look at the output impedance of the VRM when it's off, the VRM is not turned on, then all you will see is the capacitance, the bulk capacitor's capacitance. And from that downward slope, you can actually see what the bulk capacitor value is. Now, when I turn the VRM on, you'll suddenly see the VRM regulating, and you will see the resistance at low frequency. And then, here's the trick. You actually have to undersize the bulk capacitor a little bit. So if the bulk capacitor is not big enough, then you will see the upward slope of the active inductance of the VRM. And then it will create that LC resonance with the bulk capacitor, and you will see a peak at the LC resonance. From our capacitor and inductor resonance equations that we showed earlier in this presentation, you can either use the upward slope of that inductor, or you could even get a little more sophisticated and look at that peak resonance, and based on the C that you measure when powered off, and that resonant peak, and also cross-checking with the inductive upward slope, it's very easy to extract out the active inductance of the VRM. This active inductance is what you need for your RL model, not the actual inductor that's on your schematic. And once you have this active inductance, it can also be used to help you with the creation of the state-spaced average model. And that's in our how-to video on modeling the VRM, or the DC to DC converters on YouTube. So please enjoy that video and learn more about making these measurements.
Great, thanks. Here's your next question from Tim. Is the best power supply the one with the lowest impedance?
We often get this challenge from a lot of our customers because they'll go and they'll look at power supplies and VRM products on the web, and oftentimes they incorrectly decide, or the power supply companies will encourage them to get the lowest impedance possible. Well, that sounds great for the power supply because the lowest impedance times the IDT will give you the smallest ripple, except for there's a problem with that. If the power supply has very low impedance, then to maintain flat impedance at the higher frequencies, we realize very quickly with our simple calculation for L over the target impedance squared that if we need to get to a very low impedance, that capacitor will become very large. And so it costs us money to have a decoupling network with a very low impedance. So if we don't need it, it's adding a lot of additional cost. So what we really want is a VRM with just enough low impedance or just the right impedance so that we don't have to overpay or add too many decoupling capacitors. And in this way, we get a flat impedance. If our VRM has a very low impedance and we don't want to pay money for the decoupling capacitors and we don't load enough decoupling, then we could get those LC resonances and peaks in our impedance which cause rogue waves. So I highly recommend loading the correct impedance for the VRM, selecting a VRM with the right impedance so that you can minimize how much decoupling capacitance you really need for a flat impedance and get the best design of impedance matching delivery to your load.
Great. Thanks so much, Heidi. And here's a question from Adrian. What is the advantage of a state space average model for the VRM?
Another great question. A state space average model of the VRM is simply a behavioral model using state space equations to represent the control loop instead of differential equations. It's a classic methodology for control loops, and the average part is because we have a DC to DC converter that's pulse width modulating the power. This state space average behavioral model allows us to have some of the resistive and feedback components in that control loop, as well as our output inductor and decoupling capacitors. With this model, we can actually start to explore tolerances of those different components. We can look at the power supply rejection ratio and really see how much noise is transferring through that VRM. And we can look at the output impedance and see how that interacts with our decoupling capacitor network. A simple RL model does not let us do this, and on top of that, the RL model does not let us look at large signal switching ripple on our power delivery network. So with the state space average model, we can get a lot of information and really do an end-to-end power integrity ecosystem simulation with the VRM control loop, our power distribution network, and the model for our sink or our load with the expected DIDT transients.
Great. Thanks so much, Heidi. Heidi, this is going to be your last question. So Davis asks, how does one measure the output impedance of a VRM or the low impedance of a capacitor?
This is another great topic that is covered in our how-to videos on how to design for power integrity, modeling and measuring capacitors and inductors. This is done with a two-port shunt impedance measurement that is essentially, it's using a network analyzer, so we can create a behavioral model over a broad frequency range. But the trick is the network analyzer has a 50 ohm impedance. And so if we did a classic reflection measurement, S11, where we look at how much of the signal is reflected back from that impedance of measuring, say, the output of the VRM or a low impedance capacitor. The 50 ohms going into that low impedance gives us a large reflection, and we don't have enough sensitivity really with the network analyzer because that large reflection is masking the small changes. So the trick is we usually connect port 1 up as sort of a Kelvin measurement excitation of the low impedance, and then port 2 is connected to the exact same location, and the small signal that actually gets through to port 2, it's sensing across that low impedance, and the small signal that makes it to port 2 is a very small, very sensitive measurement of changes of that impedance. And so if you want to learn more about this two-port shunt impedance measurement technique, please watch the how-to video. And sorry I don't have more time to answer more questions.
Thank you for attending today's webinar brought to you by Keysight Technologies. Join us next month for the continuation of our Engineering Education webinar series, and enjoy your day.